Okay, so what is cloud? I think we don't want to explain that. It's a kind of utility. So it's becoming a utility after water, electricity, and gas. This is my definition. You can have a look later. Okay, so this is the hype cycle. You may be familiar with this. This is the Gartner hype cycle. They actually produce this hype cycle almost every year. So every technology comes and then it goes up to the top, then there is a trough, and then stabilizes. So that's the theory. So where does cloud computing starts in this hype cycle? We can see that, sorry, how do I get up? I don't have the, do I have the, where is that? Here it is. Okay, so cloud actually is actually coming down. This is where it starts, which means that it's going to actually stabilize in the course of time. It's going to be a part of our lives. So this is the state at this stage, the right scale, that is a cloud portfolio company. So they think that this is the state of the cloud, and last year or this year, you can see that, public cloud and private is actually, private cloud is getting a kind of traction. So it's a good thing, and so that is a hybrid cloud. Just for the information's sake, as I think Tripod was telling, the big players, I think Amazon, the Rackspace, we can't see any small players here. That is a shame. And again, when we go to the private cloud model, we can see that here we got a bit of hope, because at least 3 of them are open source projects like OpenStack, then CloudStack, then Eucalyptus. They all are open source projects. So that is a kind of consolation for us. Okay, and again, one more thing, the OpenStack is actually gaining a momentum. That means in 2014, last year, I think that made a lot of strides forward, which is again a consolation. So when I talk about cloud, I think personally, in a private cloud scenario, I look to OpenStack rather than any other cloud middleware, just for the information. Okay, now this is the question. Okay, can we have SPC in cloud? That is a very classical question, and the answer is very evident. Some say that it is not possible. It could be possible, and mostly, Gartner again predicted in 2011, 23% of the computing activity would never, ever will move to cloud. And Ian Foster, I think from Argonne, would also say that this is true. And the HPC applications are the ones which are not supposed to move into cloud. But is that the end? There is a silver lining in the cloud. There's always a silver lining. Okay. Even that is a fact. I think there are possibilities that some specialized clouds could provide something different, and that's why I will actually explain a little bit of the Docker and how that is going to actually help us maybe. And there are some projects like Science Cloud supported by Nimbus. That is an open source project again. So they all are looking into the possibility of using cloud for HPC applications. Okay, so these are the 2 questions I think very relevant. One is whether the cloud could produce HPC or near HPC performance, the near HPC performance. And then next, whether, this is the question which I'm interested in, the second one, whether HPC capabilities of a cloud can be harnessed, can be accessed effectively over internet. So the use case is something like this. Yesterday, I think there was a guy from Fujitsu, and he was telling, he was presenting the idea of a high-performance smartphone. So then that was mostly into improving the performance of the chip. But my question would be, okay, if I got a smartphone, can I use it like a supercomputer? Because can I connect my smartphone to a supercomputer, maybe in the cloud, and then can I actually use it like a supercomputer? That is my question. Okay. So the first question, okay, in order to answer the second question, I think we need to go into the first question, because whether the cloud can give near HPC performance, So for that, there is a Dell Experiment. What they've done is they've created a kind of scenario where a bare metal installation with Red Hat, and then again a virtual machine running OpenStack. So on a single machine, on a single node. And then they ran NAS parallel benchmarks and some other applications like ANSYS. And the results are applications which are embarrassingly parallel, they actually perform 1 to 2% lower than the VM. So if they are embarrassingly parallel, 1 to 2% on the VM. And then applications which are high memory bandwidth, that requires high memory bandwidth, so like conjugate gradient or something like that, they perform 25% lower on VMs relative to bare metal. Here, one thing, you have to be very careful, they're actually running it on a single node. So that's why I think they're getting that kind of performance. So I had an experiment when I was doing my PhD 2 years back. So I tried in the n-body solver, the n-body solution, and I ran that on Vayu, that was the cluster available at Australian National University at that time. Now they actually got a bigger one, but anyway, at that time we had that cluster. Then I ran the same on Rackspace, that's a public cloud. And I ran that on, four machines with 4 instances. So that's important, like running on multiple machines. Then the performance, I think, it took nearly half the time, double the time. So that means the performance actually went down. Okay, so how do we cut the fat? So if that is the case, is there a possibility of having HPC, near HPC performance in the cloud? I think the answer is already been shared a little bit. I think Docker is a way to look into this kind of solutions. Okay, I think it has been discussed, so I will skip through these slides. The background, we all know that is basically Linux LXC, then Google had similar kind of projects in the past. I think even Oracle Solaris had concepts of containers in the past. And this is interesting for me as a researcher, I would say, because here we are cutting the fat, like the hypervisor is gone, and actually the Docker is running on the host OS. That means it is lightweight, and we expect that there could be performance improvement. That means if the cloud runs Docker, theoretically, we would expect some kind of performance improvement. Okay, so this is something about Docker again. Okay, this is how the fat is being cut. That means it's running on the bare metal Docker. So that's the advantage which I'm seeing. So the loading time and the system resources that need to launch these applications could be lower. That's a theory. Is it practical? Okay. So then I again resort to an IBM experiment they've done by Mr. Borden, and again, he gives us a disclaimer. These are passive tests, like without any tuning analysis, etc., etc. But I think it will give some idea whether it is possible. Okay, before that, what OpenStack is. I think I will put these slides because these are there. I don't want to discuss OpenStack here now. Okay, but important slide is this one. Okay, we can actually put Docker on OpenStack. So OpenStack is a cloud middleware. So we can say that we can actually hook in Docker into cloud. So this is how we do it, according to, I think, Docker itself. And this is what they've done. IBM software is basically OpenStack. So I've talked to the IBM guys in Bangalore. So they said that IBM software is built on top of OpenStack. Okay, so this is how they did the experiment on OpenStack and KVM, then OpenStack and Docker. And these are the performance improvements that they actually produced. This is just for the boot times. So average server boot time, then the compute, I think for the Docker it's very less, and memory footprint is also very less. So this is the only available data which I got, and this is also from IBM, not mine. But this gives me some kind of insight to say that, cloud could actually produce near HPC performance at some stage, with addressing all the security concerns, etc., etc. In fact, in the future, not now, it could. But with that premise, I worked on something 2 years back during my PhD. So whether if cloud has got that HPC capability, can I actually access it, harness it over the internet? Just using a smartphone or something. So that was my question. So this is a kind of surprise byproduct of my PhD. Okay, so what I did was I was working with a service-oriented architecture middleware that was platform Symphony. Later on, that was taken up by IBM. And what I will explain. What did I do? Okay, just an introduction to service-oriented architecture, just to get an overview what I did. So SOA, basically it has got a client and service model, and in between we got a resource manager. So the client actually asks for the resources, then the compute is being done at the service instances on different machines or the same machine. Then a resource manager actually allocates the resources. The scheduling is done by the resource manager. And my project was basically with scientific applications. And in scientific applications, the main problem is the interdependency. So I think most of you know what is the issue. That means if the data is dependent on the other one, after each step it has to go back. So there is a kind of synchronization we need to happen in between. So they are called the generations of tasks. So generations of tasks. So they are not embarrassingly parallel. So this is a problem. An n-body problem, classical n-body problem. With this, using this example, I'll try to explain what I was just trying to do. N-body problem, we all know the universe or maybe the solar system, and if I know the positions and velocities of these elements, I should be able to predict the positions maybe hundreds and thousands of years in the future. Okay, so the conventional approach, how do we do it? I got a known set of values, mass and velocity and position, and then iteratively I do the calculations. I find the mass, velocity and position for the next time step. Then I synchronize the data. Then again I do it. Then synchronize the data. I go like that. So that's how I have to do it. Okay. So this is how it will be done in the conventional SOA model. So the client asks for the resources and gets the resources, and then client actually sends tasks to service instances, and the partial computation is done. Once the partial computation is done, the services get back to the client, and all the partial computations are at the client. Once that is there, it synchronizes all partial results, and then we go for the next generation. So that's how it is being done in the traditional way. Okay. Now, here the problem, every time we have to come back and then do the thing. That means a lot of communications. When we got a lot of communication, it kills the application. It kills the performance. So that was the problem which I was facing. So how to circumvent this problem? So we introduced a kind of data service to the client and the services. It's a kind of piece of memory with a kind of addressing system. That is data service. And then the data service will allow the service instances to communicate each other without tight coupling. So that was the idea. And we hope to reduce communications. And so it will look like this. So the song with the data service will look like this. Basically common data. So the data service, data service, data service. So it's all sits, and so there is a method, there is a way to actually address this data around the service instances and client. And where it can be called using these functions again, they are pretty much, I think everybody can understand: add, get, put, and sync. And here, the put is a kind of deferred put. That is, this is the technology which we use. What we use is, okay, so we got the common data here, and if I want to update the partial updates, then each service instance can do that. But then what happens is, that is put in the common data, that is put in a kind of different piece of memory with its metadata, and along the time, once the sync is called, then I update the common data on my service instance. And then, if at all there is a kind of data, change in the data in the other service instances, that is also reflected at that time. So there is a bit of communication over there. So this is how we do it. Okay, once we got that, the model will change like this. Once we got this little bit of data service, and good thing is it sits within the same service instance or sits within the same machine. So the client actually can, client sits in a different machine. For example, that is my mobile phone, and then this could be my cloud provider. Okay. Okay, then again, request data and resources. Okay, now for the n-body problem, add the particle informations, send task to the service, and then here the service is getting the particle information from the data service, which is within the same node. Okay, and it does the partial communications, and then again puts it back actually to data service. And then there is a command isync. That means I say that I don't want to get the result here at the client. You can go ahead and you can actually do the next step and make a kind of synchronization within the cluster rather than getting back to the client. So that's a technology. So once that is done, the idea is we are reducing the number of communications, and we are trying to get most out of the cluster performance. Okay, so once we do this, we had a lot of improvements, and then I thought that I will try the same thing in cloud, and what would be the results. So 2 sets of experiments. Okay, once the first one, we did the whole stuff, we put the whole stuff into a cloud, and the client and the service instances were in the cloud, and then we found that, okay, this is the green line is the symphony model, that is a traditional model, and this is the new model. Okay, the traditional model is better, it was much better, a little bit better in the cloud, and the symphony model, the new model is not performing that well, but still that is within the cloud. But then when we did this, that means the client was outside, and then we had the service instances inside the cloud. Okay, now the conventional model, that is the NBS Symphony model, it jumped. That means it took nearly something like 300, 400 seconds to do the same work. So the performance was very low. And then we did the new model, and then again it took a little bit more time. Earlier it was nearly 11 seconds, now it is 20 seconds. And here we can see it takes a bit of time, and this red line is basically the initial loading time. That actually goes up, but that is only for the first step. But after that, I think we can see that we are getting acceptable level of performance. So this is a comparison. So the comparison is very stark here. Like the old model, it's up here, and the new model with the common data or the data service, that is up here. Okay. The inference is, yes, it is possible, and there could be a way in the future where we should be able to access the HPC capabilities of a cloud over the internet, which could actually help us to make smartphones or handheld devices kind of a supercomputer. So we will have some applications which can harness the capabilities of cloud or a supercomputer over the internet. That could be possible with these kind of models in the future, but it is only kind of prototype. We haven't done anything over that, and maybe somebody will pick that up. So I think with that I will stop my presentation. Thank you so much.